This is the video for section 2.2, separable equations. And we are finally, after 2 weeks into the course, ready to solve our first class of differential equations. So here's a question for you to get us started. How do I solve the differential equation dy dx equals x squared plus 2x? Now this is actually the simplest type of differential equation to solve. We can solve it using the fundamental theorem of calculus, and so we can integrate both sides and we get that y of x is x cubed over 3 plus x squared plus some arbitrary constant c. So seeing this is going to motivate how we will solve slightly more general differential equations called separable equations. The definition is as follows. We will say a first order ordinary differential equation of the form dy dx equals g of x times h of y is called separable. So here the quote-unquote right-hand side of the differential equation can be written as the product of two functions, one of which depends only on x and the other depends only on y. And if we have a separable differential equation, we will solve it using what's called separation of variables. And I'll demonstrate that later in the video. So first, let's make sure we can write down examples of a separable ODE versus non-separable ODE. So take a second, write one down. Here's what I came up with. Y prime equals y squared times cosine x plus x cubed. So my y squared is my h of y, and cosine x plus x cubed is my g of x. A non-separable differential equation would be something of the form, for example, y prime equals y squared plus cosine x plus x cubed. There is no way to write that as the product of two functions, one of which depends only on y, the other of which depends only on x. So that one we will not be able to solve using the techniques in this section. So here's the idea of separation of variables. Let's suppose I have a separable differential equation, so dy dx equals g of x times h of y. Now this is what I am going to do. I'm going to say, okay, well, that means that dy over h of y equals g of x times dx, and I'll just integrate both sides. Right? Well, you may feel like there's some trickery going on here because dy dx, even though it looks like a fraction, it's not really a fraction. The creators of the notation of calculus were really, really smart, and they made notation very, very suggestive so that things like this, things like separation of variables, look like it's just multiplication and division of fractions, but that's not fully what's going on here. So even though this is how separation of variables are going to work, we need to do a little bit more to prove that in fact this works the way it looks, and we'll do that in class on Friday. So let's take an example. Let's solve the differential equation dy dx equals minus x over y, and the initial condition will be y of 1 equals 2. First thing to ask yourself, is this a separable differential equation? And you'll see, yes, indeed it is. So I use separation of variables. I multiply the y on both sides, and I multiply the dx on both sides, and I'm saying that in quotations even though you can't see me. So I have the integral of y dy equals minus the integral of x dx. I integrate both sides. I get y squared over 2 equals negative x squared over 2 plus c, and I'm just going to absorb that arbitrary constant all on one side rather than having plus c1 and plus c2. We'll just put all of the plus c on the right-hand side. So that means x squared plus y squared equals some constant. Now I use my initial condition, y of 1 equals 2, and I can solve for c. So c should equal 5. So our solution, it is located on the curve x squared plus y squared equals 5. Now you might ask yourself, why did I say our solution is located on that curve rather than being x squared plus y squared equals 5? Well, the first thing is x squared plus y squared equals 5 is the equation of a circle, and so it is not a function. And since we want our solutions to be functions, we know that this whole circle cannot be our solution because it doesn't pass the vertical line test. That's the first thing. Second thing is that our solution is not defined at y equals 0. If we go back to the differential equation, the right-hand side was minus x over y. That function is not defined at y equals 0. So remember from our existence and uniqueness theorem, that means that our solution can't possibly be defined there. So indeed, we get that our solution is the upper half of the circle, and we eliminate the points on the y-axis. And you can see that if you solve it explicitly, for y, you get plus or minus the square root of 5 minus x squared. Since our initial condition was in the upper half plane, we take the positive solution. And since we know our solution is not defined at y equals 0, our interval of solution is negative square root of 5 to square root of 5, the open interval, so not including those endpoints. Now, I will give you a word of caution. It is possible to lose a solution using separation of variables. So we always need to be careful that we are checking the hypotheses of the existence and uniqueness theorem before we willy-nilly apply separation of variables. And here's an example of what can happen. Let's take the differential equation dy dx equals x times y to the 1/2 with initial condition y of 0 equals 0. So right away you should be able to see that there is one solution, y equals 0, the constant solution. That's a solution to this initial value problem. What you might also notice is that this differential equation is separable. So we can solve it using separation of variables. So I take the integral of dy over y to the 1/2 equals the integral of x dx. I integrate, and I get y to the 1/2 equals x squared over 4 plus c. And notice here, I'm going to make the caveat that c has to be greater than or equal to 0. So when we solve differential equations, really when you do anything in math, you have to be careful about what information you're being given at each step. Notice at this step, we have y to the 1/2 equals x squared over 4 plus c. X squared over 4 is always greater than or equal to 0 for any x. Y to the 1/2 for any real number y is also always greater than or equal to 0. So there's no way that I could have a c value that is less than 0 and still make this function well defined. So I'm just making that observation for us here, because in the next line I'm going to lose that information. So y equals the quantity x squared plus 4, x squared over 4 plus c, quantity squared. And here, notice if I had not been keeping track of the fact that c was greater than or equal to 0, c could have been anything. So I'm just keeping track of that so we don't lose any information. Now, my initial condition was y of 0 equals 0, so that means that c equals 0. So my solution is y equals x to the 4th over 16. Now, of course, we also already saw that the constant solution y equals 0 solved this initial value problem. So we have two solutions, and thus we do not have a unique solution passing through 0, 0. And the reason is, if we go back to the differential equation, we see that the function that we call f in the parlance of the existence and uniqueness theorem is x times y to the 1/2, and of course df dy is not continuous at 0, 0. So that's why we did not get a locally unique solution at that point. So in summary, separation of variables, if we just did it without checking the criteria of existence and uniqueness, we lost a solution. But if we are in a scenario where the existence and uniqueness theorem is satisfied, like if y of 2 equals 1, then we don't have anything to worry about. Separation of variables will not lose a solution. So we can go back to where we were before, y to the 1/2 equals x squared over 4 plus c. And if we use our initial condition, we find that c equals 0, which means that y equals x to the 4th over 16 is the locally unique solution through the point 2, 1. In class, we will see even more examples of separable differential equations, and we will get to test our skills with remembering integration formulas.